And yes, last time my microphone sounded like crap on the recording. I have no idea why. I keep troubleshooting things, and I think I make it worse every time I fix it. But this one works better. And this is not a Windows 11 computer, so everything should work seamlessly, if I can remember to work it correctly. So, apologize for the quality of the recording. I will try to do better next time. So, let's look at the beach for a second, where there is no snow, also. More coming tonight, by the way, so good times.
Like how much? Because I'm supposed to drive to Michigan tomorrow. Like, am I gonna have to go look at the weather?
Anyone? Can we pull up the forecast? Has it
I'll
changed?
figure it out.
Like 3 inches, maybe? I think I saw.
I think so.
1 to 4.
1 to 4. Yeah, there's always a range, right? Yes. So that means I will have to say goodbye to my mailbox, I think, after today. There's just only the little top of it poking out of the snowbanks right now. Yeah, the American dream is to own a house, people tell you. No, the American dream is to be inside your apartment sipping coffee while someone else plows your sidewalk for you. That is the American dream. Yeah, so you're not missing anything, those of you who don't have to take care of property right now. It is not fun. Anywho, what did we talk about last time? What do you remember? I'll accept letters, words, gestures, pictures, if you can find a way to do that. What's this class about? Okay, we got shy people.
So one of the first things that we discussed the other day was how this sort of fits in with ANOVA and where that's looking at some categorical traits, and we can have either univariate or multivariate cases of that.
Yes?
And how, depending on the types of predictors we have, the name changes a bunch.
Yep.
And so even though it's one big umbrella, we have like 6 different names that we can be using.
Yes, so within the general linear model, there's variations on the name based on what kind of predictors are in it. But that makes it more confusing than it has to be. So yes, what we're working on is building a taxonomy of how things relate to each other and how the names map onto combinations of things. So in the course that you just finished, or had finished at some point prior to this, regression, right? We typically would call it regression if you're predicting an outcome that's continuous, and you're doing it with one or more quantitative predictors. If we throw categorical predictors into the mix instead, we would call that ANOVA, or analysis of variance, or analysis of covariance if you have a mixture of the two. But the common denominator really is what kind of outcome are you predicting? Now, what if you have an outcome that's not continuous? Can you do that? Can you predict something like whether or not a student graduates? You do that, right? Undergrad outcomes? What outcomes do you care about in your research? Give me some examples. And Zoomers, you can talk to me or you can type in the chat, and I'm watching that as well. Give me some outcomes. What do you care about? Students' GPA. Okay, is that a continuous variable?
Yeah, I would say so.
You say so. What's the highest GPA you can have?
4.0.
4.0? What if I try really, really, really hard? Can I get something above 4.0?
I mean, in some countries,
Yeah.
the highest criteria is often 4.5 back in Korea.
Okay.
But yeah, but there is always a boundary.
There's always a boundary. Yeah, you can have AP courses that tack you above. And I think in the grading scale here, if you get an A+, then you go over 4 in your GPA.
4.2.
Yeah, I give out A+, by the way. Just putting that out there. I'm more than happy to help you boost up your GPA to compensate for a B or C at some point. I do give A+, just putting it out there. So yeah, you have a boundary. So is it continuous?
Continuous?
Uh-huh.
Continuous, but with boundaries.
Continuous with boundaries, yeah. So I call that continue-ish.
Right.
That's what I call that.
Yeah.
So you need a regression model that understands that 4.0 is the end of the scale, or 4.5 if you're in Korea, for instance. Right? What's the lowest GPA you can have?
0?
0. So there's another boundary.
Yeah, right.
Yeah. So your regression model needs to understand those boundaries. even though there's numbers in between. It's numeric, and I would think of it as interval, but there's boundaries. What else? Sarah, you're from psychology, right? Undergrad? What kind of research did you do as an undergraduate? Did you help with anything?
Yeah, kind of. I was kind of thinking about I'm doing a project with school-based mental health interventions, so maybe like depression and anxiety or something.
Depression and anxiety, probably measured as some kind of scale score or potentially latent variable.
Yeah, or like trying to like reduce it, I guess. Could potentially continuous.
So that's another one that it's kind of in the same boat, in that it's continuous. It's definitely numeric and interval enough, probably, for purposes. But if somebody answers the lowest possible response to all the questions, right, that's a boundary. And if somebody answers the highest possible response, that's a boundary. So it's still, like in practice, something that we want to make sure the model understands, that you can't predict anything higher or lower than those boundaries. Anyone study categorical outcomes? Like whether or not something happens? Or what kind of like major you pick, something that's nominal like that? Anything like that? Can we do that with a regression model? Can I predict the likelihood of someone graduating or dying or, I don't know, let's go with something more fun. The likelihood of snow? Oh wait, that's not fun.
Winning the lottery.
Winning the lottery, the likelihood. Oh yes. See, if you buy 2 tickets, you're twice as likely to win the lottery. Yeah. You've moved the decimal over like from the 100th spot or whatever, maybe to the 99th spot. So regression models for categorical outcomes then definitely have to look different, right? Because you're predicting the probability of something happening, where it's, again, boundaries. But the thing you're predicting is either one or another. So there's no way that could possibly be continuous or continuous even. But can we do that? Can we predict any kind of outcome we want to?
Maybe not any, but you can predict most.
A whole lot of them, yeah, a whole lot of them. Watch me remember to start the screen share myself. I am winning. Here's some types of outcomes. So this class is called generalized linear models, and "ized" means not normal something else. That's what it means. General models are a special case. So we are going to go through a whole bunch of different combinations, starting with binary. That's the one that's easiest. It's the starting point. Ordinal or nominal, build on binary. They use the same machinery to do it, but you add multiple equations for each possibility of choice that you're predicting. These I call categorical, but any of these other synonyms would apply. So discrete variables, qualitative variables, grouping variables, factor variables is what they are in program like documentation syntax. A class variable if you're using SAS, IDOT, and Stata, and so forth. And then like these kind, quantitative variables that aren't truly continuous, they have natural boundaries. So percent correct or number correct on a test. Things like GPA, because you still have, it's a range, but up to a point. Or scale scores that have floors and ceilings based on the lowest possible response pattern or the highest possible. Counts, those are very common. They have special names regarding whether 0 is possible. So if you have a count that doesn't have any zeros possible, that's called 0 truncated or 0 altered as a synonym. If you have more zeros than expected, it's 0 inflated. And I call these if and how much, because at that point, what you're predicting is whether or not you have a 0, and then how much if not 0. So there's a lot of outcomes that look like that, particularly if you're mixing populations. So if you're looking at something like one's history of abuse as a child, you can ask a whole bunch of questions, and somebody who had a nice, happy, well-adjusted childhood will be like, nope, 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 that didn't happen. I got a 0. And then there's other kids who did not have it so good. So in that type of model, it actually would become 2 different outcomes. Were you abused? Are you a 0 or not? If you were abused, how bad was it? So you don't have to think of it as one variable. It's both qualitative and quantitative differences across people at the same time. There's a model for that. Censored is sort of related to these. There's a model for that as well. So yeah, there's all kinds of distributions and models that go with different outcomes. And there's others that aren't even on this list. So for skewed data, for instance, that's continuous. So this is where I think we left off, maybe? That sound about right? Okay. So the Legos, there's another thing. Remember the 4 Legos? The building blocks of quantitative methods, according to me and Jonathan. Lego number 1 is linear models. You're going to get very, very good at that by the end of the semester, especially interaction terms. Yep. They're important. The ability to be able to take a research question and figure out how to set up your model so it directly answers your questions is a skill. And that skill persists across any type of model, across any type of sampling design, across latent variables and observed variables. Linear models run the world. So that's building block number 1. We're going to get a lot of practice with that. Number 2 is changing how we estimate the models, which is how that is required in order to add the other blocks. So regression, as you learned it before, uses least squares estimation. That's the manner in which the model decides what the optimal parameters are, the ones that minimize the errors, the sum of squared errors. We're going to use instead, what did I say we were going to use last time? 2-word phrase, first letter M, second word, first letter L. There's your clues. It's abbreviated ML, so. Maximum something. Likelihood, yes. In one word, what does maximum likelihood do? I'll take gestures. Vladimir's drawing likelihood functions in the back of the room. Or else he's surfing. Yeah, peak, I'll take that. I was going to go with height, but yeah. Yeah, maximum likelihood is the machinery by which we figure out what the best version of the parameters are given the data, from the data that we have. And the formula for height changes as a function of what your outcome is. So if you have a continuous outcome, you use the normal distribution as your formula for height. What if I am doing a repeated measure study where I have multiple outcomes per person? Can I do that? Sure I can. Should I change my formula? Probably, because if I have multiple outcomes from the same person, they're likely to be related. So then my formula for height needs to understand that, and I need to switch to a multivariate normal distribution instead. If I have binary outcomes, different formula for height. If I have count outcomes, different formula for height. But it's still the same principle. That's the way that we decide, not just within a model, which parameters should be the output, but then across models. Okay, I added 2 new predictors. Did it make my data taller or not? If it did, I win. And so we can compare models and how well they fit and judge the utility of additional contributions to them through that. So that's estimation, changing estimation into something that is iterative is number 2. Number 3 is link functions. That's what we're going to start talking about here soon. A link function is a transformation, but it is not a transformation to the data. We are not taking our data and log transforming it or anything like that. What we are doing is transforming the conditional mean of the outcome to be predicted. I know that's a mouthful, but the purpose of it is to make it so that we take something that has boundaries and we stretch it out into infinity. But there's a conversion back to the bounded version. So the model will understand that we can't have a probability above 1, for instance, or we can't have a GPA above 4. Then, if it's not normal, what should it be instead? We pick a different distribution, and that's our formula for height. So linear models still run the world. That's this square right here. It works the same. It's just that now we're predicting a different version of the outcome directly, so that that version is the continuous version. Here's a quick example. I'm on slide 26 in lecture 0 here. Okay, so I'm predicting the probability of winning the lottery. We'll go with that one, something nice and happy. And I have a model that says that I think the probability of winning the lottery is a function of X. What would predict winning the lottery? Number of tickets. So if I buy 9 tickets, I am guaranteed to win the lottery. That's what this picture would say. Maybe that's a little too happy. But look, guess what happens if I buy 10 tickets? I have a 120% chance. And down here, if I only buy 2, I have no chance. I have less than no chance if I only buy 1. Now, this doesn't make a lot of sense. What we need is a picture that looks like this. We need it to get bendy, logisticy. How we get that way is a link function. Some genius figured this out a long time ago. Welcome to your new best friend for the next month or so, the logit. The logit is a transformation of probability. Inside here, we have the probability that y is 1 divided by the probability that y is 0. That interior part is called odds. What are the odds of winning the lottery relative to the odds of not winning the lottery? Odds is bounded at 0 but goes into positive infinity. So we've solved half the problem in terms of probability having boundaries at 0 and 1. And then some genius figured out that, hey, if you take the natural log of this thing, then you're into this lovely new metric called logits, or log odds. I say logit. I've heard various other pronunciations. My first graduate student from the University of Nebraska to actually finish used to say it's logit, because you don't take the log, you take the log. He's not wrong. In certain fields, log odds is much more common than logits, but this is an example of a link function. It takes probability that is bounded between 0 and 1 and translates it into something that is continuous and unbounded so that we can predict it with our regular linear model. So if I made a picture of predicted logits, that line is straight. When I take the predicted logits and back translate them into probabilities, it looks like this. It's magic. Other link functions you may have heard of. Probit, also known as ogive, just logs by itself. So for count outcomes, are count outcomes bounded? The number of times something happened. Number of lottery tickets you purchased. What if we wanted to predict that? Who is likely to buy more lottery tickets? What's the fewest number of lottery tickets you can buy? 0. That's how many I buy, because I believe that lottery is a tax on people who are bad at math. What? I said what I said. I don't play the lottery. I don't. So I am 0. Now, how many lottery tickets can one buy? If they're just wildly optimistic and or not great at understanding probabilities. I don't know, like infinity, as many as the store will sell you, there's probably an upper limit of what they're legally allowed to do, or at least I hope there is. So counts have a one-sided boundary. So we don't need to do the interior part for counts, we just take the log. And that stretches out the bottom part into something that's continuous. So logits and logs are like the main ones that we will use in generalized models. There's others, but they're less common. Their job is to translate the predicted outcome into something that is truly continuous so that when you back translate it into its original metric, it stays in its boundaries. That's a link function. The reason that general linear models are considered a special case of generalized models is they say that the link function is identity. Okay, you majored in math, right? Or stat? What does identity mean to normal people?
To like a non-statistics perspective,
Yeah.
I'd say identity is what we perceive something as.
Yeah, but I wasn't going that far away. Yeah, 1. Like the identity. 1. It's an identity link. That means leave it alone. Times it by 1. That's what an identity link is. So from that perspective, what you learned as traditional regression is a generalized model using an identity link and a normal conditional distribution as one choice. But here's all the other choices. So here's the alternative distribution if it's binary. There is no possible way that a column of zeros and ones is going to ever be normally distributed. It's not going to happen. There's only two possible values. So a distribution that describes a column of zeros and ones is Bernoulli. That's a person's name. That's why it's capitalized. And it's the simplest one. Height for this is the probability of a 1 if that's what you got, or the probability of a 0 if that's what you got, the end. I know that if 75% of my sample got a 0, I know that the rest of them had to get a 1. 25% got a 1. All I need to know in this distribution is the mean. There is no variance. The reason for that is that variance is tied to the mean. The probability of a 1 times the probability of a 0 is your variance. And this is your skewness. It is non-constant. So in the middle of this table is a probability of 0.5. That is where the variability around it is maximal. As you move either direction, it shrinks until you get down to the ends here, where if the mean is 1, we call that a constant. A degenerate distribution, as from what I understand. That one always makes me laugh, because it sounds like a put down, but no. And this one too. So a normal distribution does not work for binary because normal distribution says there's one variance, right? And it's the same for everybody. There is a different variance depending on what your probability of a 1 is. It's not constant. But this distribution understands that. Now, a consequence of this, though, is that if it's not constant, it's not a number that we can say we had this much variance and now we have this much. Because we don't have it as a separately estimated thing. It's tied to the mean. So that means that all of the effect size things that you learned related to variance accounted for, remember that? What am I talking about? There's a letter. Amount of variability your model predicted, or proportion of variability your model predicted in your outcome. What's that called? R. Yeah, R squared. Yeah. That is in regression, that is really straightforward because there was this much variance in Y to start with. We put these predictors in, it went down by this much. Yay, we win. It's gone. For binary data, it's gone. There is no more residual variance as a separately estimated thing that goes down. So that means that we have to come up with different ways of doing effect size. Variance explained is no longer a thing. And it will not be a thing in this class. Like, it's just gone. Because the normal distribution is pretty much the only one that has a separately estimated variance. The rest of them, the variance is a function of the mean. So that changes the logic a little bit. Here are your choices. This is a picture of Mr. Potato Head. Do they still play with these? Anyone know what this is?
I do.
You play with them? So Mr. Potato Head has like slots where you put body parts. And this one is put together correctly, more or less. But I used to take like the eyes and put them in his mouth and vice versa and like make him look like, you know, crazy Frankenstein Potato Head. But I like this picture because that's how I think of these models. It's like plug this in and now I need this and I'm going to plug this in. So if I plug in a logit link function and a Bernoulli distribution, then I can predict binary outcomes. If I plug in a logit link function still, but a different distribution that has more than two choices, multinomial is more than two choices, whereas Bernoulli is only two, then I can predict ordinal or nominal outcomes, where the difference between them is what flavor of logit that I use, basically how I set up multiple submodels that predict the differences between the categories. If I have proportions, like percent correct or something, that's still logit because proportions are bounded between 0 and 1. But now I have a different type of distribution because proportions are continuous between them. So GPA would look like this, for instance. Anything that is continuous in the middle but bounded. Binomial or beta binomial would probably be the distributions I go to with that, potentially with zero inflation. Counts, it's our friend log, because counts are bounded only one way, and log fixes the negative side and leaves the positive side alone. Then what kind of distribution does it take? Usually something within the Poisson or negative binomial family. We'll see those. Censored outcomes use something called TOBIT. So yes, logit, probit, TOBIT, they all rhyme. And either a normal distribution or potentially a normal paired with a Bernoulli for the probability of being censored as a separate thing you predict. Skewed continuous, I don't have a name for that, but the log link makes sure that things stay within above 0 if that's necessary for that type of outcome. And either a log normal distribution for the residuals or something called gamma. Bimodal distributions, beta distribution works well for that with the logit link function. And then zero inflated, all of these. So it's like plug and play. And once you figure out like what family you're in, then the rest of it is relatively straightforward. So it's very much a taxonomy. Each of these distributions implies a different formula for height. So we can still do maximum likelihood to figure out all of the parameters. So here's what is going to be different then in terms of moving from standard regression as you know it for continuous outcomes to generalized extensions for any other kind of outcome. You can still include whatever fixed effects of predictors you want. So whatever slopes you want. Those slopes can be linear or nonlinear. You can have grouping variables, doesn't matter, whatever you'd like. Here's the differences though. This whole like ANOVA versus regression versus ANCOVA, all of those distinctions are gone. The only thing that matters in these models in terms of naming it and describing it to people is what kind of outcome you have. There's no special names if you have categorical predictors versus continuous predictors. The linear model predicts the transformed outcome directly and predicts the original outcome indirectly. So for binary data, the data set has zeros and ones in it, right? That's the original. The conditional mean to be predicted of a binary variable is the probability of a 1. So now we're moving a little bit further away from the data. Our model is not going to predict probability directly because probability has boundaries. It's going to predict the logit or the probit of the probability directly because that's unbounded. So you can work backwards through the chain to eventually get back to the zeros and ones, but what the model is doing is predicting the transformed outcome conditional mean. So you just have to remember that when you're interpreting these things. F-tests, remember those? Like you get an F-test for whether your R-square is significant. You might get an F-test for whether there's any group differences across your categorical predictor. The way those used to be computed was with sums of squares stuff, but sums of squares are gone. We're not using that. We're using maximum likelihood, but we're still going to have some Fs. However, sometimes those Fs will turn into chi-squares instead, and their univariate analog of t for testing one slope at a time is going to turn into z. The difference is that generalized linear modeling software usually does not allow the use of denominator degrees of freedom. So estimate divided by standard error is a test statistic that we'd normally treat with the t distribution. It switches to z in these models. Likewise, F is how you test multiple slopes at the same time. That switches to chi-square. F times the number of slopes you tested is chi-square. There's a one-to-one correspondence, but you'll see different test statistics on your output because of that. And then last but not least, if we don't have a separately estimated variance, we don't have an R-square. So there's R-square is gone, and that means anything related to R-square is gone, like semi-partial and partial eta squares for effect sizes, all that stuff's gone. But we're going to get some stuff back. I'm not just going to leave you hanging. We're still going to look at effect size, just differently. All right, so what do these models replace? Things that people used to have to do before they had maximum likelihood available at a moment's notice, even on their phones. Data transformations. So, how do I put this? There are textbooks that have standalone chapters on data transformation. I'm thinking of a particular multivariate book, but I know there's others. That is a terrible idea. You would never want to transform your variables in the absence of a model. In particular, it's the residuals that are supposed to be normal in regression, not your original variable. So there's no point in transforming them anyway until you know what your residuals look like. Bye, folks. So we're not going to transform the data. We're going to transform the mean to be predicted instead. And that happens in the machinery of the model. That's not something we do. So these are examples of transformations that people used to do to get around non-constant variance or to have an outcome that is continuous. Non-parametric statistics. We're not doing those either, sorry. Those are least squares based workarounds for violations of normality, but they also have assumptions that are not likely to be reasonable, such as the same type of non-normal distribution holds across groups. I liken this to a course on VCR programming. This is probably something that you would have needed in the 1980s. We don't need it anymore. Generalized models are how these things get done most of the time. Very occasionally, if I have a really, really small sample size that has repeated measures or other complexities, I might resort to some of these if I have like no choice. But a principle-based model would be our first pick for all of these things. All right, so that's a good place to pause. How we doing? Zoomers, still with me? Roomers? Doing okay? Thumb poll. Question? Okay, your question and then your question.
So I understand the concept of not wanting to transform the data because we're more worried about the residuals. But if we need to implement some type of transformation due to like the scattering in the residuals where variance increases as some predictor increases or something like that, at what step would we want to implement a correction if we want to implement one at all?
So the question was, understand that we don't transform data, we're concerned about residuals. And I'll add to that by saying we're not concerned about distributions at all when it comes to predictors. They do not have distributional assumptions. They can be whatever they want to be. If you see that your variance increases, like that fan shape that we had, a model-based solution to that is going to work better than an ad hoc sort of transforming thing. So it's not common, but there are models, they're called location scale models and multi-level models, where you can actually take your residual variance and create a linear model for it. Like, not explain the residual variance, explain how much there is of it. And you can say, I think the E variance increases as a function of X. And that, you can do a hypothesis test. And you can say, or you can say, I think residual variance is higher in this group than in that group. So you can build that into a model. So the transformation things I think are is if you have no choice, like if you're in some sort of situation where there really isn't a good strategy, then that's when I would implement that. But you have to have a model first, would be the main thing.
Yeah.
Does that help?
Yes.
Or answer? Okay, your question.
When you're talking about data transformations, are you talking about data transformations for both predictors and outcomes, or is this mainly a outcome conversation?
The only time you would really need to do it is an outcome, like, because predictors don't have distributional assumptions. However, if you have a predictor that's really, really skewed, you might be concerned about influence or leverage of like the extreme points pulling the line, or alternatively, if you have a predictor in which you think more is better but up to a point and then it kind of levels off, if you log transform that predictor and put a linear slope in of the log transform predictor, that creates that bendy line instead. And that would be a reason to transform it, is to get the shape you want, not necessarily to fix it.
Yep. Great, thank you.
Okay, other questions? Yes.
Can you explain the part where you say they are under non-parametric statistics, they may require rank transformations first, as in like that whole part?
Yes, so a Spearman correlation is a Pearson correlation done on data in which you have said the highest score is, or the lowest score is 1, the next lowest score is 2, the next lowest score is 3, and you've like squished it. So you're losing information about how far apart the values are, which is usually like that should matter. Like, why would you want to destroy part of the information in your variable? And so a lot of these require some kind of rank transformation as part of it. And they also, like, they still have assumptions. It's just they're changing what they are. These are things that people used to have to do because they didn't have a choice. They didn't have the computing. We've got the power now. We don't have to do that anymore. Okay, thumb quiz. How we doing? Are we feeling optimistic? This is how optimistic are you feeling about the semester? Okay, mostly up. That's good. All right, so towards the end of the semester, we're going to take these models and extend them for multiple outcomes. Now, why would we want to do that? Various situations, such as you're thinking of your outcome as a single variable conceptually, but you've got more than one of them. So classic example, longitudinal research. Several of you mentioned that, right? You doing longitudinal research? I teach longitudinal classes. That's my jam. That's my bread and butter. It's coming back in the fall. Like you might think of, I'm going to measure, give me something that changes over time. Anything.
The number of credits a student attempts.
Okay.
Semester.
The number of credits a student attempts in this semester. So I'm thinking of number of credits as my outcome variable. But if I have fall and spring and fall and spring and fall and spring, then I have 6 of them. And in all likelihood, those 6 versions of the same thing from the same person are going to be correlated. So multivariate models are ideal when you have one outcome, but you have more than one of them per person, because you have to tell it, hey, these are from the same person, they're going to be related, and there's different ways you can introduce those relationships. Same with repeated measures of other kinds. So if I want to see how well you do on some task while you're listening to Metallica, and then I play classical music, and then I have silence, right? I might have condition A, B, and C of something. The outcome is the same, but it's under different conditions. Those are going to be related because they're from the same person. So multivariate models then are necessary for those. If you are doing family or dyadic research, right? If you have multiple people from the same family, do you think their outcomes are going to be related? Probably, especially if you're studying, say, partners and you're looking at relationship satisfaction. Theoretically, how satisfied I am in my relationship should correlate to some extent with how satisfied my partner is, hopefully. So those types of designs require multivariate models to look at everything at the same time so that you can build in those correlations. Also, research questions that involve comparisons of effect size. So let's say that I'm starting an intervention study. I'm trying to reduce maladaptive outcomes for people, but I think my intervention is going to be more effective on anxiety than it is on depression. In order to answer that question, is there a stronger intervention effect on one outcome than another? They both got to be in the same model. Then I can answer that question. And the last one, mediation, if you're interested in indirect effects. My intervention is going to fix this problem, and fixing this problem is going to improve this other problem. That type of causal chain in terms of logic, you need all of the variables in the model at the same time to do an optimal way of analyzing that. So these are all examples of when you would turn to multivariate models, and we have the same choices available to us as in univariate models. What kind of outcomes do you have dictates how they get predicted. So ordinary least squares for multivariate models quickly becomes useless. First biggest one, no missing data. If I have a longitudinal study and I want to run a traditional repeated measures ANOVA, it list-wise deletes anybody who doesn't have all the outcomes. Bad for power, bad for inference. It also only has 2 choices for the correlation pattern across the outcomes, all different or all the same. Intermediates are likely to be more useful. And it requires balanced data, meaning everyone has to have the same possible outcomes. So switching to maximum likelihood solves these problems too. You can keep whatever partial information you have on somebody. They don't have to have all the variables for the data they do have to contribute to the model. It does require a change in software, though, to be able to do this. So this is where we will pick up M+ towards the end of the semester. Also R-Lavon and Stata's SEM package can do these sorts of models. These are considered path models, path analysis, which are relationships among observed variables only in a multivariate framework. And learning all of this stuff is going to set you up to take further courses. So we're going to focus on linear models add link functions to predict different kind of outcomes. The way that that is possible is by switching how we get the answers to maximum likelihood and height-based estimation, where we can plug and play different distributions for how height is computed. Then, those things are all essential prerequisite building blocks for content in multi-level models, factor analysis, structural equation models, item response theory, and these are the course numbers in our program that go with those things. So multi-level or mixed effects models are when you are predicting outcomes in multiple dimensions of sampling at the same time, such as kids who are clustered in classrooms, who are clustered in schools, repeated measures from the same person who might be clustered in things. So they're useful in a whole lot of different contexts. And measurement models, confirmatory measurement models, then use all of these things too. So hopefully, my intent is that by going through this course and picking up these three pieces, that when you need to pick up the fourth Lego, the random effects and latent variables, that's the only new part. And then it's not so much at the same time. So there's my sales pitch. Are you sold? You're like, well, it's required, I have to be here, so yes. I'm hoping that I can make it from I had to take it to I got to take it. That's where we're going with this. We're going with enthusiasm. And that's that. All right, that's the end of my sales pitch. I'm going